Assalamualaikum and a very good day to our respected lecturer. My name is Nurul Aisha binti Mama Ishaq from Group 9. Today my group members and I are pleased to present our industrial power system analysis covering our laboratory work from Lab 1 to Lab 7 and a summary of our assignment on Isan furniture manufacturing. The presentation will be divided among 4 presenters. I will cover the introduction and Lab 1 and 2. My colleagues, Hairul Izham will present Lab 3 to 5. Muhammad Wazi will cover Lab 6 and the assignment issues. And finally, Muhammad Nabil will present the proposed solution and conclusion. Here is our presentation outline. We will cover 7 laboratory sessions followed by the assignment issues, proposed solution and conclusion. The labs progress from basic load estimation to advanced power system simulation using ETAP software. Each lab builds upon the previous one, giving us a comprehensive understanding of power system analysis. Let us begin with the first lab. In Lab 1, we estimated all electrical loads in the furniture factory. We collected data on 41 pieces of equipment and classified them by voltage level and duty cycle. The table shows the 10 largest loads in the factory. The total connected load is approximately 1,600 kilowatts. The loads are distributed across 4 voltage levels: 6.6 kilovolt, 3.3 kilovolt, 415 volt, and 240 volt. This load data become the foundation for all subsequent calculations, including transformer sizing, cable sizing, and load flow analysis. Let me explain the transformer sizing process in Lab 2. We started with 41 loads classified by voltage level and duty cycle. The calculation followed a step-by-step process using utilization factors and diversity factors. First, we applied the utilization factors to each load. This accounts for the fact that not all equipment operates at full capacity at the same time. Second, we apply diversity factors to group load on the same distribution board. Third, we apply to group distribution board at the same voltage level. And fourth, we apply KS3 of 0.9 to combine all load at the main switchboard. Finally, we added 65% for future expansion and selected the nearest standard transformer size. For the 6.6 kilovolt load, the calculated SKU was 571 kVA. After applying all diversity factors and future expansions, we selected a 1000 kVA transformer. For the 3.3 kV load, the total SKU was 1075 kVA. This is the largest load group, so we selected a 1250 kVA transformer. For the 415 volt loads, the total SKU was 431 and 35 kVA. For 431 kVA, after applying diversity factors and future expansion, we selected a 500 kVA transformer. In summary, all 3 transformers are properly sized for current and future loads. T1 is 1000 kVA for the 6.6 kV bus. T2 is 1250 kVA for the 3.3 kV bus. T3 is 500 kVA for the 415 V bus. With that, I will now pass the presentation to my colleagues, Hairul Izham. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Hairul Izham bin Muhammad Zaidi. My metric number is AN230033. So today I will explain about Lab 3. So in Lab 3, we designed the complete one line diagram as we can see in the slide. the one-line diagram using IPS software. So the diagram includes the utility supply from TMB 11 kV. After that, the 3 transformers, the main bus at 11 kV, distribution bus from SPDB 1 to SPDB 9, and then 41 loads including motors, lighting, and office equipment, and also cable size appropriately, and protection device such as circuit breakers and relays. This one diagram shows the complete power flow from the grid to every load in the factory. The diagram was built in IPS software and used for all subsequent simulation. So next I will explain about lab 4. So in lab 4 we size all the cables based on load current and voltage drop equipment. We use BS7671 table VD4D4A as our reference standard. The table shows that cable size selected for each voltage level. For the 6.6 kV level, we selected 50mm cables rated at 163 amps. For the 3.3 kV level, we selected 25mm square, and the cables rated at 102 amps. For the 415V level, we selected 10mm square cables rated at 58 amp. For the 240V volt level, we selected 2.5mm square cables rated at 31 amps. So we also checked the voltage drop for the longest cable run of 250 meters. So the voltage drop is 2.2%, which is below the 4% limit. This means all the cables are sized correctly and voltage drop is within acceptable limits. So next for the lab 5 is, in lab 5 we run the initial load flow simulation. The requirement is that all bus must be above 90% voltage. However, we found several buses were failed in this requirement. Some of the buses were low as 47% of nominal voltage. For example, bus 116 was at 47.2% and bus 120 was at 47%. Several other buses were at approximately at 76%, and the main cause of this case is because the cables were too small and all the cables were too long and too many loads connected to one cable. So the solution is we need to increase the cable size significantly to fix all this problem. That's all from me. Thank you. So next I will explain about in lab 6. In lab 6, we increase the cable size for all the problematic circuits and we rerun the load flow simulation. The final result show all of the buses are above 97% voltage. So the SMGDB bus operate at 99.98% voltage. So the SPDB1 operates at 97.03%. SPDB2 operates at 97.24%, and all the 415 volt buses operate between 97.66 and 97.97%. The lowest bus voltage is 97.03%, which is well above the 90% requirement, and this means our cable sizing correction was successful in this lab.
The summary of the final load flow result is shown here. Total generation is 2150 kilowatts and total load is 2100 kilowatts. System losses are 50 kilowatts or 2.3%. However, the overall power factor is 0.918, which is below the optimal 0.95. This is an issue we will address later. The lowest bus voltage is 97.03% and the highest cable loading is 98.6%. Looking at cable loading, cable C2, which is 95 mm, is operating at 95.6% loading. Cable C5, which is 35 mm square, is operating at 69.7% loading. Although both cables are safe and not overloaded, the high loading leaves very little spare capacity for future expansions. In Lab 7, we designed the protection scheme including circuit breakers, current transformers, and relays. The table shows the protection equipment at each location. All high voltage and medium voltage locations have 3 current transformer and 50/51 relays. The low voltage transformer T3 has built-in protection and uses a low voltage as circuit breaker. We also design time delay coordination to ensure selective protection. Level 1 at the high voltage primary has a delay of 0.1 seconds. Level 2 at the medium voltage secondary has a delay of 0.08 seconds. Level 3 at the low voltage main has a delay of 0.05 seconds. Level 4 at the low voltage feeder has a delay of 0.04 seconds. Level 5 at the low voltage load has a delay of 0.02 to 0.03 seconds. The coordination ensures that the breaker closest to the fault trip first, minimizing disruption to the system. Now, let us move to the assignments. From our analysis, we identify 4 main issues. The first issue is low power factor. The overall power factor is 0.918, which is below the recommended 0.95. Several large motors operate below 90% power factor. For example, the hydraulic press machine is at 88.31%. The industrial beam saw is at 89.17%, and the air compressor is at 89.37%. The causes higher current, increases losses, and reduce system efficiency. The second issue is energy waste from fixed speed motors. 3 large motors run at full speed all the time, regardless of demand. These are the chiller system at 200 kW, the dust collector at 180 kW, and the fan at 160 kW. Motor run at 100% speed even when not needed. There is no speed control to match actual process requirements. This result is unnecessary energy consumption and higher carbon emissions. Let me continue with the remaining issues. The affinity law shows that for fans and pumps, power consumption is proportional to the cube speed. At 100% speed, power use is 100%. At 80% speed, power use dropped to 51%, which is saving 49%. At 60% speed, power use dropped to 22%, saving 78%. This demonstrates the large potential for energy saving with variable speed drives. The third issue is high cable loading. Cable C2 at 95 mm is at 98.6% loading. Cable C5 at 35 mm is at 96.7% loading. There is very little spare capacity for future expansion and increased thermal stress on cable insulation. The fourth issue is the absence of an energy monitoring system. There is no real-time monitoring of energy consumption. The factory cannot identify abnormal conditions quickly. This result is missed opportunities for energy saving. Now I will pass the presentation to my friends Muhammad Nabil. Thank you.
Based on the issue identified, we propose 2 main solutions. The first solution is the installation of an automatic power factor correction capacitor bank at the 415 volt main distribution board. We recommended a Schneider Electric VARSAT APFC system with a rating between 250 and 350 kVAR. The estimated cost is between 30,000 and 45,000. This solution can improve the overall power factor from 0.918 to above 0.95, reducing reactive power demand, lowering current flow, and minimizing system losses. The second solution is to retrofit variable speed drives or VSD on major motor loads such as the 200 kilowatt chiller, 180 kilowatt dust collector, and 160 kilowatt collector fan. Although the investment is higher, around 80,000 to 150,000 per unit, VSDs provide significant energy saving by allowing motor speed to match actual process requirements. This also extends motor lifespan and reduce carbon emissions. Our third solution is implementing a smart SEMS dashboard. We recommend Schneider Electric EcoStructure Power Monitoring Expert to continuously monitor power consumption, voltage profile, phase current, power factor, and peak demand. The estimated implementation cost ranges from 20,000 to 50,000 ringgit. With real-time monitoring, the factory can quickly detect abnormalities, optimize energy usage, and avoid unexpected maximum demand changes from TNB. The fourth solution focuses on upgrading cable C2. Our analysis showed that cable C2 is operating at 98.6% of its rated capacity. Therefore, we propose upgrading it from a 95 square millimeter SLPE cable to a 120 square millimeter XLPE cable. This upgrade is relatively inexpensive, costing only around 5,000 to 10,000 ringgit, but it significantly reduces thermal loading, increase reliability, and creates additional capacity for future expansion. In conclusion, this project successfully demonstrated the complete industrial power system design process using ETAP. From Lab 1 to Lab 4, we perform load estimation, transformer sizing, cable sizing, and network modeling. During the load flow analysis, we identified voltage drop problems and successfully resolved them by upgrading conductor size, resulting in all buses operation above 97% voltage levels. We also identified several key issues including poor power factor, fixed speed motor operation, thermal cable loading, and the absence of a centralized energy monitoring system. To address these issues, we propose sustainable solutions including APFC capacitor bank, variable speed drive, a smart SEM dashboard, and cable upgrades. Overall, this improvement can enhance energy efficiency, improve system reliability, reduce operating costs, and support future factory expansion. That's all from me. Thank you for your attention.